Hi everyone, I am Boyang XIao, and this is our updated version of our E542 Lab 4 video presentation, the fast reliable file transfer. We have made some modifications to our old version of our file transfer protocol to meet the requirements for this lab. There will be three parts in our presentation. The first part is the introductions, and this is presented by me. And the second part is the code and the designing ideas, which will be presented by Yixing. And the third part will be the experiments on AWS and the results, and this will be presented by Donghao. So let's get into our presentation. As we know, the file transfer protocol, aka FTP, is a standard communication protocol used for the transfer of computer files from two remote hosts on the computer network. FTP is built on a client-server model architecture using separate control and data connections between the client and the server. And an example of the FTP is the Secure Copy Protocol, SCP. So SCP is a commonly used protocol of securely transferring computer files, and it's based on the Secure Shell, SSH protocol, which is further based on TCP protocol. If we want to build a FTP, the first idea coming up to our minds are building it based on the TCP or UDP protocols. So before we get into our FTP, let's take a look at the TCP and the UDP protocols. As is known to us all, TCP is reliable, has flow control and congestion controls, but it's relatively low. Otherwise, the UDP protocol is fast and simple, but it's unreliable. So if we want to use the TCP to build FTP, it can guarantee the file transfer reliability, but it can be quite slow. Or if you want to use the UDP protocol to build our FTP, it can be really fast, but we will never know if the file is still as a whole piece on the other side. And then my partner Yixing will elaborate the code for this file transfer protocol.
Now I would like to introduce the source code of Lab 4. And the server and the client both initialize two threads to transfer data. The first thread is used to transfer data in the char array, and the second one is used to transfer ACK message, acknowledgement message. And in the client side, there is a deck to maintain the packages need to be sent. The offsite of the file is popped in the front of the deck, and then the client will read the char array. Will read the char array from the file according to the offsite, and assembling the char array with its MD5 and the offsite into the DTO. DTO is a structure used to passing by data during UDP, and the client continue to send the data until the flag and the transmission is set to be true. And another thread in client side is called update site. This thread is used to set and transmission flag when it receives the end transmission signal from the server, and also it push back offsite which server does not received and to the deck. Therefore, the deck can transfer the package one by one. And in the server side, there are also two threads, which are send ACK message and receive data. The server maintains a hash site to record the data it has not received. And if the size of the hash site is 0, it means the server has already received all the data from the client, and it will send the signal to end the whole transmission. Then the server will receive data and calculate MD5 calculate MD5 and compare with the MD5 in DTO structure to make sure there is no mistake during transmission. If the MD5 is not correct, the server will drop the package. And if the MD5 is correct, the child array will be written into the file in the server side. And as for the other thread, send ACK will always send the offsite which the server wants for the next package. And if the size of a hash site is 0, it will send -1 to indicate that the transmission is done. And if the client receives this ACK with -1, it will quit all the transmission process. And in the end, the server side will calculate the duration and the throughput of the whole transmission. And it will also calculate the MD5 for the entire output file to make sure there is no mistake during the transmission. And this is the source code part of Lab 4.
Hi, this is Donghao Zhao. In this part, I will present you the behavior of our fast, reliable file transfer program. The demonstration will consist mainly of 3 parts. The first is an introduction of our AWS environment. The second is the network configuration and the network measurement. The third is the file transfer demo and the performance of our program. We are using 3 interfaces on AWS to emulate our network. The client and the server are running Ubuntu operating system. The router is running vivaOS operating system. The client is connected to the router through the network 1, and the server is connected to the router through the network 2. 3 public IP are associated with the interfaces so that we could use SSH to control them. The file that we want to transfer is on the client machine. So it will run the client program to send the file to network 1. The router will forward the traffic to the network 2. Finally, the server will gather the packets, assemble the file, and save the file. So in order to see the performance of our program, we enforced some limitations on the 4 network interfaces, such as bandwidth, delay, and loss rate, so that we could simulate the bad network scenario. The result will be present shortly. So this is our VPC topology. Now we are connected to the instances through SSH. The client is on the left, the server is in the middle, and the router is on the right. And the routing table is showing the network topology that we just discussed. So in the first case, we want a network condition that has maximum transmission unit of value 9,000, 10 milliseconds of round trip time, 1% of loss rate, and 100 megabits per second of bandwidth. So first, we change the MTU using these commands on all virtual machines. Second, we limit the bandwidth on all virtual machines using these commands. Finally, we are going to enforce the network delay and drop rate by these commands. Great. Now we have our desired network conditions. To prove that the network conditions are correct, we are going to use iPerf to do the network measurement. First, we show the MTU by using if configure on all virtual machines. We can see now the desired network interfaces all have MTU 9000. Second, we ping from client to server to show the round trip time. We can see now the round trip time is around 10 milliseconds. Third, we use iPerf to measure the TCP throughput. We can see that the TCP throughput is approaching 100 megabits per second. Finally, we use iPerf to measure the UDP bandwidth. Here we can see the UDP bandwidth is about 100 megabits per second. Now we can see that we have the desired network condition. Now we are going to transfer the file using our program. There is no need to demonstrate the file transferred under all 6 cases. You can find the result in our report. So here we would like to demonstrate the worst case, which is when MTU is equal to 1500, round trip time is 200 milliseconds, loss rate is 20%, and all interfaces of the sender, receiver, and router have a bandwidth of 100 megabits per second. First, we set the limitation on all machines. As you can see in the screen, the limitations have been set properly. Second, we start the server program on the server side and then start the client program with the destination IP of the server and the file path as the parameters on the server side. We can see now the transmission has been started. Now let's wait for the transmission to finish. After a few seconds, the transmission has ended. We can see the duration and MD5. The MD5 are matched, and the whole transmission usually takes around 235 seconds, which will give us of around 35 megabits per second of throughput. In this report, we listed the detailed procedures to compile and run our program. And how did we tune the network for different network conditions, which are here and here. For case 1, we have gone through the case 1. In here, you can see the network measurement summary for case 1 and the screenshots as the proof of the measurements. Then we listed the result for case 1. One thing I need to mention is that if the MTU is 1500, we need to change something in the code, which is here, basically to reduce the size of packet from 5000 to 1400, and also change this to the server side. Then for case 1, for the result of case 1 on page 8, our throughput reduced under the case where MTU is 1500, basically because the network can't allow jumbo packet. For the result of case 2 on page 11, our program takes a very short time to finish transmission compared with SCP. The throughput is lower than the case 1, but still much better than SCP. For the result of case 3 on page 14, our program works well and also better than the SCP. So, in a word, our program can outperform the SCP on almost every case. There are many places that we can make it better, but we don't have enough time to implement them. We will continue tuning this program to get higher throughput. Here we conclude our laboratory 4. I hope you enjoy this video.